like to thank a long list of collaborators, and including Jörg Baylor, who will be giving the second talk of today. Now, I would like to start with the big picture. So what is the biggest problem in computational physics? So actually, the answer was already given by Paul Dirac almost 100 years ago. So Paul Dirac said the elementary laws necessary for understanding materials and chemistry are largely known, meaning the Schrödinger equation is known. But the problem is that the solving of these equations are just too complex to be trackable. So what is the solution? Again, according to Paul Dirac, the solution is to develop approximate methods so that we can simplify these computations. And with that in mind, let's look at the state-of-the-art methods. So I'm arranging the quantum mechanical methods on two axes, so the cost and accuracy. So you can see there's a sharp trade-off between the cost and accuracy. And the more accurate the methods are, more costly it is. So the workhorse of the field, the so-called density functional theory, has a good balance between the two. However, even with that, we can only handle systems with hundreds of atoms on a time scale of picoseconds. We can use empirical force fields, but typically they lack quantitative accuracy. But when it comes to materials modeling, the problem doesn't just stop there, because it's not just the energy and forces of the system that we are interested in. It's also about the entropy. So here in Vienna, we have the Boltzmann's grave, and on his gravestone, it's engraved the Boltzmann's equation, and it reads as the entropy is equal to the Boltzmann constant times the logarithm of the number of microstates. And the microstate is a specific realization of the system. It contains all the information about the coordinates and the velocity of all the atoms. And this so-called Boltzmann's equation, unfortunately, is not completely correct, because in reality, we not only need to count the number of microstates, but we also need to weigh them appropriately using Boltzmann's distribution. Now, but nevertheless, the point here is just that to be able to accurately assess the entropic contribution of the system, we need to exhaustively sample all the relevant microstates, which of course imply a very high computational expense. Now, this is where the machine learning potential come into rescue, which is pioneered by Bela Palinello, and also together with there's another work by Albert Bartok and Gabocciani and co-workers. So machine learning potential is supposed to sit in this magical spot that it has the low cost, but also an accuracy that is on par with initial methods. So put these into numbers, instead of being able to handle system size of hundreds of atoms, we can really go large. And more importantly, the scaling of the system compared with a cubic scaling, typical cubic scaling of density functional theory calculations, a machine learning potential usually follows a linear scaling with respect to the system size. Okay, so I will first like to provide a very kind of black box view on why machine learning potential works at all. So the idea would be that I have a training set of atomistic configurations, and I basically provide labels. So I compute the energy and forces using a quantum chemistry method. It can be DFT, but it can also be something else. And then I use a machine learning method. In this case, we plot neural network, but it can be anything else, such as linear regression or Gaussian process. And after the network is trained, when a new structure comes in, and the machine learning algorithm can provide speedy and hopefully also accurate predictions for the energy and forces. And this is a sort of a black box view, and I find this type of view sometimes unsatisfactory. And now I'm going to provide a different explanation of why machine learning potential works at all. Now, if I invite you to take a look at these two atomistic configurations shown here, right, what would you see? And you might be thinking, okay, the one on the right looks like a solid, and the snapshot on the left looks like an amorphous liquid. And the reason why you may be making this observation is because on the configuration on the right, if you focus on individual atomic environments, meaning that if I sit on an atom and I look at the neighboring atoms around me, like all the atomic environments are very similar. In this case, it's FCC, face-centered cubic crystal environments. However, if we look very, very closely, there are also very similar atomic environments in the liquid. And we might even be finding solid-like environments in the liquid configuration as well. And I shall come back to this point a little bit later. Now, of course, this is very hard to see with naked eye, but fortunately, the community has developed many so-called representations. And perhaps Michele Chariotti and other people have talked about it in the previous days. So we can represent this environment using a list of vectors, using a mathematical representation, and then we can compare and characterize them with ease. Now, what does it mean that, what does it sort of imply that we have very similar atomic environments over and over again in our system? This means that if we do the traditional ab initio molecular dynamics way, this is kind of wasteful. The reason is that we encounter these repeated atomic environments. So we don't have to recompute them over and over again. Instead, we can be like, okay, let's say I have a memory, and each time I encounter a new atomic environment, I just memorize what this environment looks like and what are the energy and forces associated with this environment. So next time, when other environments comes in, I can just make a comparison between the new environment and the ones in my memory. And based on their similarity, I can make a prediction for the new environment. Of course, this hinges on the nearsightedness of energy and forces of each environment. So to summarize, how do we construct a machine learning potential? It is basically a two-step procedure. First is that we collect a whole bunch of atomic environments as diversely as possible. And the machine learning part is really a more like a sophisticated way of interpolating between the environments that are in our training set. Okay, so with that, I would like to jump to some applications. The first system is the system of water. It's of course a very common ubiquitous system, but it still has many unresolved mysteries. So for example, we know the liquid is densest at 4 degrees Celsius. And ice floats on water, which is a little bit unusual because solid is usually a little bit denser than the liquid. And then there's also subtle differences between light water, H2O, and the heavy water, deuterium water. Ice is also very highly morphic, and the two ambient pressure phases, hexagonal ice and cubic ice, if we do a density functional theory calculations, the two have almost identical lattice energy. But we know in nature, all the snowflakes and ice cubes are made of hexagonal ice, meaning hexagonal ice is more stable, but theory is not able to provide an explanation. So we use the Baylor-Palinello framework and train the potential based on a hybrid DFT, RAP-B0, D3 level theory. And I just want you to take a small mental note on the composition of the training set. So the training set has about 1,500 bulk liquid water configurations, okay? And so for water, just the potential energy surface is not quite enough. And the reason is that so the hydrogen is very light, and the hydrogen atom usually have very strong nuclear quantum effects, and the nuclear quantum effects can influence many aspects of our system, such as the free energy, hydrogen bonding, diffusivity, and so on and so on. We usually treat this using the so-called path integral molecular dynamics algorithm. And one thing I would like to highlight is the so-called quantum kinetic energy. So we know, classically speaking, right, because of the equipartition theorem, like all degrees of freedom in our system should contain the kinetic energy of kBt in each degrees of freedom. Now, so for example, for this water molecule, you have the OH bond stretching, and then the breathing mode, and also the out of the plane vibration of the hydrogen atoms. Classically, they should all contain the same amount of energy of kBt. However, because of the mostly due to the zero point energy and other nuclear quantum effects, this is most definitely not the case. And you can see for each mode contains more than kBt, and depending on the intrinsic frequency of the mode, each mode also contains a different amount of kinetic energy. And combining these two pieces, and then we can look at some of the theoretical predictions compared with experimental measurements. So here I'm showing you the density isobar, and the dashed line is from classical molecular dynamics simulations, neglecting nuclear quantum effects, and the solid ones are using path integral molecular dynamics, basically considering nuclear quantum effects. And so this is for ice, and then we have liquid water, then we compare with the experimental measurements. So we can see that more or less the theoretical predictions are within a few percentage of experiments. And we also capture the density maximum of liquid water very well. And another observation is that nuclear quantum effects actually makes water a little bit denser. For me, it was a little bit counterintuitive. We can also look at the radial distribution function and compare with experiments. Again, here we need to turn on the nuclear quantum effects to get a very good agreement with experiments. And we are most interested in the thermodynamic properties, so namely the free energy. And for doing that, we use the method called thermodynamic integration. And if we look at the thermodynamic integration expression, it almost kind of trivial. It's basically saying that if we have two systems, system A and system B, and if we can find a thermodynamic path connecting these two systems, then the free energy difference between them can be written as collecting the differential difference along this path, right? So it looks like almost a trivial statement. But in practice, because of this flexibility of picking the thermodynamic path, this is thermodynamic integration is an extremely versatile and useful method. So typically for computing the free energy of a solid system, we usually start with the harmonic reference, because harmonic systems have analytic free energy. And then we use first thermodynamic path to go between the harmonic system and the classical system. And then the second path to go between the classical system with the classical nuclei to the quantum mechanical nuclei. So this way we consider nuclear quantum effects. And coming back to the last part, from the classical to the quantum nuclei, essentially we are doing an integration, making use of this aforementioned quantum kinetic energy. And now I'm going to show you something that it can be a little bit disturbing. So we did the free energy calculations for the ice phases. And now I'm showing you the chemical potential difference between cubic ice and hexagonal ice. I'm showing you the results computed using two different fits of the neural network potential. And you can see the results disagree, and they don't just disagree sort of quantitatively, there's also has the opposite sign. Of course, to put things in the perspective, we are talking about the energy scale of a milli electron volts, and that's extremely tiny. But nevertheless, how can we actually claim like our estimate is at the true ab initio level if it depends on the specific fits of the machine learning potential? So, so the problem, the sort of to resolve this, what we want to do is that we want to promote the potential energy surface described by the machine learning potential to the true DFT level. The two potential energy surfaces are extremely similar, but there's still a tiny a bit of a difference. And we not only want to do this correction for one configuration and one point of the potential energy surface, but to do this for the whole potential energy surface. And to put this mathematically, we can, so this is actually a free energy perturbation approach. So we can, the difference between the Gibbs free energy of the system described by DFT and the ones described by the machine learning potential. So the difference between them can be written as the average of the exponential of the difference difference in energy of configurations sampled using the machine learning potential force field. So, and after we add this correction term on top, and we can see we are reaching a statistically converged estimate for this chemical potential difference. So to summarize the overall workflow, so apart from the upper part that I have described before, in the end, we always add a correction term to promote our estimate to the true ab initio level. So, and now I'm just plotting out the magnitude of this correction term. And in general, the correction term is very small, so on the order of milli electron volts, but it's there, and it's also temperature dependent as well as dependent on the specific phase that we are studying. So coming back to the results, so to compute the chemical potential difference of hexagonal ice and cubic ice, we first do this estimate at the machine learning potential level, and we add the correction term to bring it to the DFT accuracy, and then we also consider nuclear quantum effects. So overall, nuclear quantum effects significantly stabilize hexagonal ice and make it ever slightly more stable than the cubic counterpart. So without nuclear quantum effects, perhaps the snowflakes in nature will not have six-fold symmetry. And the next example is the chemical potential difference between ice and liquid water. So the same story, we computed using the neural network potential. Here we are using umbrella sampling to do this estimate. And then we correct it to a DFT, and then we consider nuclear quantum effects. So we can also consider separately for D2O, the heavy water, and H2O, the light water. And we can also compare with experiments. So overall, we are extremely close to the experimental measurement of the melting point, and moreover, we can even capture the difference between the melting point of D2O and H2O, which is about like 4 Kelvin. Okay, so at this point, some of you might already have the question, right? So I was using the machine learning potential that was trained entirely on liquid water to predict the property of the cubic ice and hexagonal ice, but how is that possible? And moreover, there are many more ice phases out there, and can a machine learning potential be used for those ice phases as well? So to prove that, we collected the exhaustive set of ice phases. So we collected 54 phases of ice, and this include all the experimentally confirmed ice phases, apart from the very high pressure ice 10, and also the hypothetical ones people have proposed over the years. And now I'm showing you just a PCA map that visualize the similarity between these 54 ice phases and the 1,000 liquid water configurations. So basically on PCA map, things are close means the structures are very similar, and things that are far apart means the structures are different. Now, and in general, we can distinguish between ice and the liquid water, which is kind of understandable since they are structurally different. One lacks long-range ordering. However, the interesting thing happens when we instead not compare the overall structure for these phases, but instead just compare the aforementioned atomic environment. So we set a cutoff of a 6 angstrom, and we only compare these small atomic environments. And in this case, the environments in ice, which are plotted using the red and the pink dots, are almost entirely covered by the diverse environments from the liquid water configuration. So the liquid water are these blue ones. So what does it mean? This means that when we are training on liquid water, right, we have already collected all the environments that are pertinent for the ice structures as well. So coming back to this construction of the machine learning potential, the network has already had the information, has already collected the environments for the ice configurations. And so to prove this, so we compare the predictions of the machine learning potential with DFT calculations and also experiments. And in all cases, so we compare the density, lattice energy, and the vibrational property, namely the phonon density of states. So in all these comparison, the machine learning potential predicts very well all these properties. So this is a big panel. It's a little bit hard to see, but we can zoom in and see the phonon density of states are very well described by the machine learning potential for the low ambient density and high density and low density ice phases. And because the machine learning potential is able to predict well the property of all these ice phases, we also use the machine learning potential to explore the water phase diagram. So we computed accurately the chemical potentials for all the 54 ice phases. So back then we were hoping of predicting stable ice phases that were not observed experimentally, but we are slightly disappointed that it just happens that the low chemical potential phases predicted by the machine learning potential are all experimentally known phases. So this was a little bit disappointing, but on the other hand, it also testified the completeness of the experimental phase diagram of water. Okay, so the usual, we did our usual trick. We promote our prediction to the DFT level and also considering nuclear quantum effects. So here we are. So this is the first ever phase diagram of water based on the DFT level of theory. So here I'm showing you the phase diagram of water based on this hybrid functional REP-B0D3. And also using alternative functionals, namely PB0D3 and B3lib D3. And we can see at these hybrid levels, we are very close to the experimental phase diagram, and particularly for the low pressure part, and particularly for the lower pressure part. And this level of prediction is actually much more accurate compared with the empirical water models. And moreover, the nuclear quantum effects usually shifts up and down the stability by about 5 millielectron volts per molecule. And at high pressure, this can really move around the phase boundary. This is just to compare the phase boundary of H2O, D2O, and the classical water, assuming point like nuclear. Okay, so if you think the example on water is very mundane, and you are probably right. So here I'm going to show you a more exotic example. So now we travel into the outer space and look at planets. So inside the planets, these are in our solar system. We have a high pressure and temperature environment, and if you look at the Neptune. In the mantle of Neptune, the main composition is water, and under the very high pressure and temperature environment, the water is not like the liquid water that we are used to, but it will turn into the so-called superionic water. So what is superionic water? So in contrast with the Mickey Mouse molecule, water molecule that we are used to, in superionic water, so we have the oxygen that occupies a crystalline lattice. Right, it can be BCC or FCC or HCP, and the hydrogen atoms behave like a liquid, so it just diffuses around in the oxygen lattice. And so we have this sort of qualitative picture of what superionic water is, but however, it is not known what are the stability conditions for superionic water. And moreover, because there are many competing oxygen lattices, so it's also not clear. So which form is the one that is inside the giant planets like Neptune and Uranus? So for that, so we carry out the computation. So again, using a machine learning potential. So let me walk you through this plot. So essentially at low temperature, between, let's say, 20 to 400 gigapascal, the stable form is the so-called ice 10. So this is a sort of a familiar form, and it's insulating. But upon increasing the temperature, we in this very small region above the BCC superionic transition temperature, we have the superionic BCC ice. And then the most part of the phase diagram is occupied by the FCC superionic phase and the hexagonally close packed HCP superionic phase, and I'll go back to this part a little bit later. And above the melting temperature, we have a ionic liquid. Now, what this phase diagram can tell us is that if we also plot out the internal condition of Neptune and Uranus, this basically tells us what is the composition of water in these planets. So basically we're saying that, okay, if we go inside the core of Uranus and Neptune, if we go along the radius, so we will first have ionic water, and then inside, and after the temperature and pressure reaches like this threshold, and then in Uranus and Neptune, then it switched into the superionic FCC and HCP. So between FCC and HCP, we also computed the chemical potential difference between them. And the result is like the chemical potential are extremely similar. And the difference is on the order of 10 milli-electron volts per formula unit. And indeed, that because it's so similar, if we start a growth experiment, if we have a slab, right, in the liquid water, and we let the crystal grow, it will grow into a mixed packed sequence. Because the chemical potential are extremely similar. And the next example, we switch to Jupiter. So inside Jupiter, the main component is hydrogen, and on the surface of the planets, the pressure is still low, and we have the familiar di-molecular hydrogen. But when we go into the center, the pressure ramps up, and then the hydrogen becomes metallic as well as atomic. So again, we have a machine learning potential to model this process. So we have the black line here is the melting line, and the color scheme here shows you it's an order parameter that measures how bonded the hydrogens are. So the blue means that the system is mostly molecular hydrogen, and the red shows that the system is mostly atomic hydrogen. So we observe the smooth transition between molecular hydrogen to atomic hydrogen, but then we also want to understand the physical process of this a little bit better. And we used the so-called regular solution model that describes the mixing of two fluids, because in our case, the hydrogen fluid can be understood as a mixture of atomic fluid and a molecular fluid. So using a regular solution model, the total Gibbs free energy of the system as a function of X. So X is the composition. We can think of X as the fraction of a molecular hydrogen. The Gibbs free energy can be written in three parts. One coming from the chemical potential difference between the two phases. And then the second part is the mixing entropy. When we have two fluids and then we mix them, we have an entropic gain. And then the third part is the enthalpic penalty of mixing. And the reason is that when we're mixing two fluids, and because they're not ideal, and the non-ideal effects are captured by this third term. Right. So from this regular solution model, so we will have three pictures, three scenarios. So when the temperature is high, you will have the perfect mixing of the two fluids. And when the temperature is low, it's below the critical temperature, then we will have the spontaneous phase separation of these two fluids. So now we would like to understand what is this G of X for our system. And we computed just that. We computed this G of X for hydrogen as a function of molecular fraction at different conditions. And then we fit the results to the regular solution model in order to extract the two parameters for the regular solution model. So this delta G is the chemical potential difference between the two phases. And also omega captures this enthalpic penalty of mixing. And from this, then we can determine where is the critical point of our system. So the critical point is plotted here using this green star and happens just to lie on the melting line of the system. So basically, basically above melting, the system behaves like a supercritical fluid without any first order phase function. And in the last example, I would like to show you, so we switch gear a little bit. Instead of talking about thermodynamic property, I would like to talk about the transport property. So I'm going to talk about heat conductivity. So heat conductivity measures how fast a material can conduct heat. And of course, this is a fundamental metric that is relevant in a number of processes, such as fluid dynamics and the modeling of energy systems and so on and so forth. Now, the traditional way of computing the heat conductivity uses the Green-Kubo relationship. So the Green-Kubo relationship is basically by integrating the autocorrelation function of heat flux. And this is actually a little bit problematic because notice that this integration goes from time equal to 0 to time equal to infinity. But if we have the autocorrelation function computed from our simulations, inevitably this comes with a little bit of noise. Right. So if you actually integrate to the infinity, you will have a divergent estimate. So that's not feasible. So in practice, people usually cut off somewhere. But that, of course, introduces a systematic bias because the autocorrelation function can have a long decaying tail. Now, but that's not all of the problem. And another problem is that the heat flux is actually a not well-defined quantity for atomistic systems. And if we look at the expression for the heat flux, it has two components. So the first component uses the atomic energy. So it's the atomic energy times the velocity of each atom. And the second term is the pairwise interaction between two atoms. And both of these guys are not well defined. And the reason can be understood that because the atomic interaction are intrinsically long-ranged and intrinsically non-local. and many body. So there's no unique way of pinpoint what is a localized atomic energy. And because of the many-body nature of atomic interaction, it's also difficult to assign a pairwise form for the forces. Now, indeed, in practice, so remember, like for machine learning potential, we go from the atomic energy defined for each local environment, but this is more like a mathematical construct rather than a physical reality. So for example, here I'm comparing the atomic energies predicted using two different fits of the neural network, and you can see they are very different. They are not correlated at all. And so this is for the system of water. And first I was thinking, okay, maybe if we look at the molecular energy of water molecules, this gets better, but that's not the case. Even the molecular energies for water molecule, for the bonded water molecules, are not well defined. They are like different between different fits of the machine learning potential. And however, we find an alternative formalism to compute the heat conductivity. So essentially, we start with the particle density field. The particle density field is just based on the instantaneous coordinates of the particle. So it's a very well-defined quantity. So we can do a Fourier expansion for this particle density field. Essentially, we just only rely on the coordinates of all the atoms. It turns out that if we use the hydrodynamic equation, turns out the density field, the particle density field encodes the information about heat conductivity. So more explicitly, if we look at the correlation function of this particle density field, this is already expanded on the wave vector k, and this correlation function would have two modes. One is an exponential decay mode, so this first term here, that is related to the heat propagation. And then the second mode here, which is oscillatory, correspond to the sun propagation. So which means that if we can capture, if we can just compute the autocorrelation function of the density waves, which we can very easily from our usual MPT and these simulations, we can fit the autocorrelation function to this expression and extract out the heat conductivity and also other quantities if you would like. So we did just that. So first we did a benchmark on Lennard-Jones system. So we can see the dashed line is from simulations. It's the correlation function of the density wave. And then we fit to the solid line fits to the hydrodynamic equation. So you can see the quality of the fit here. And alternatively, we can also do this in the power spectrum. So in the power spectrum of the waves, that's also okay. In which case we have two modes. The one close to zero are correspond to the heat propagation, this exponential decay mode, and then the second mode is the sun propagation. But they are equivalent. Okay, so what we do is we compute we extract out the heat conductivity at different wave vector k, and then we extrapolate to k equal to 0 limit, which then give us the macroscopic heat conductivity. We can compare because we are still working with Lennard-Jones, and for Lennard-Jones, it is still possible to compute the heat conductivity using Green-Kubo. So we can also compare with Green-Kubo results, and they are very consistent for all the conditions that we have considered. And then we can, but because but our method only uses the particle coordinates and only uses the equilibrium molecular dynamics simulations. And we can use this for more complex systems where Green-Kubo would fail. So for example, we compute the heat conductivity of the high pressure hydrogen fluid. And this is described by a many-body machine learning potential. Again, we compute the autocorrelation function of the density waves, and then we fit to the hydrodynamics equation, and then we extract out the heat conductivity. Okay, so I would like to stop here and welcome any questions. So I hope I have convinced you that machine learning potential is a useful tool to bridge the gap between first principle calculations and thermodynamic as well as transfer properties that are hard to compute. But of course, there are still plenty of open questions and how to best construct and utilize machine learning potentials, especially considering that our systems, the atomic interaction, we use the locality assumption, but in reality, there's also long-range interactions in our system. And moreover, I showed you an example of using liquid water configurations to train ice, to train the machine learning potential, and the machine learning potential can then be used for ice. And are there other cases where there's extrapolation and the generalization works? And overall, I think this is a very exciting time for the computational prediction and perhaps even design of materials. Thank you.
Thank you. So now we take questions. Bingqing, I have questions already, so but I want to give other people a chance to ask questions. Okay, Bingqing, thank you very much for the talk. And so water is not boring, it's very interesting. There are some people that have been studying water all their lives, so this is very important for all of us. So thanks for the talk. So I have a question. Your density of water from machine learning is lower than the experimental density. Why do you think this?
I think this is probably due to the fact that although we are already doing hybrid DFT, but this is not but we are still making some approximations. So the residue difference between theory and experiment are probably due to the inaccuracy of our DFT calculations.
So maybe if you include long-range dispersion, because you need the density to increase, right? So if you include long-range dispersion, maybe that will help to bring the molecules together. Do you think?
It's very hard to it's very hard to imagine things like that. But on the other hand, like I think like it's also the machine learning potential doesn't just, it's not like it neglects long-range interactions completely, right? So it's basically treating the long-range interaction in a mean field kind of way, right? So it try to capture the long range within, like it try to sort of have a mean field approximation of the long range and include that in this sort of compact short range description. So it's very hard to imagine like what would actually happen. I guess one can do a experiment of fitting a potential to the long range empirical water model and compare.
Okay, thanks. The other question I have, actually two more questions. One is the fact that the energy of each atom or each molecule from machine learning does not match the one from ab initio calculations. Can you force it to match? Like set that as another condition so that when you do the green kubo, you can just use the energy per atom from the machine learning. Can you force it?
Okay, so there are two aspects here, right? So first of all, I don't think atomic energy is a well-defined quantity at all. Like regardless whether we are talking about ab initio or empirical force field or machine learning potential, this is because okay, so you have a you have an atomistic system, right? The interactions are intrinsically non-local, right? Let's just imagine the simplest case, right? So we have two atoms here and they have some interaction. Right now you are going to assign an atomic energy to each atoms, right? So let's say we have this bond, right? I can assign the energy to be 50-50 of this bond energy to the two atoms, but it's also equally valid to assign like 30-70, right?
Okay. Yeah, but in your next slide, your next slide you compare with DFT, no? In your next slide.
No. So in DFT, it's not possible to have atomic energies at all, right? Because we only have the total energy of our system.
Yeah,
So they
so this,
just compare the energies from two different fits of the machine learning potential
oh,
to
okay.
prove the point that in machine learning potential, although we do have this concept of atomic energy, this is more like a mathematical device for us to help us fit the potential energy surface rather than a physical reality.
Okay, I agree. Yeah, thank you. Professor Jamako has a question.
Yes, hello. The question is more philosophical. We were discussing with Omololu about how we see the future in the field, because indeed, I mean, let's take someone that doesn't know the different models that exist for fitting into atomic potentials. I mean, it's still nowadays something that it's complicated to choose the correct one, to choose the correct structures on which, to do the DFT calculations. There is those methods that are now the learn on the fly, where you combine ab initio and the learn of the, and then you continue the dynamics with machine learning to atomic potentials. But those are limited in the size by the calculation that you do with DFT. So how do you see the future in the sense of, when do you think that we could have something that is a bit more automatic, where basically we can do as in DFT, and the only thing that we have to care about is the exchange correlation functional and and having a reasonable size of the cell. Thank you very much.
Right. So I think that this is a very important and a fundamental question. So my personal take I have a sort of two personal views. One is that I think we ought to sort of develop a method that can quantitatively assess whether long-range effects are important and what is the intrinsic complexity for specific systems. I think we need to develop methods for that. And then the second thing is that regarding the fitting of the potential. So right now the methodology we have are like are a little bit artisanal, or we will say semi automatic, right? So even when we are using like learning on the fly methods, we still need to decide which molecular dynamics we run and what conditions to collect these configurations, right? So I think the field ought to develop methods that make this process more rigorous, and moreover, there's also a lack of quantitative assessment of how good a machine learning potential is. So for example, for traditional machine learning, then it's easy to compare, right? We look at the error of the prediction, right? But for the case of machine learning potential, we also care about the generalizability and as well as the stability. And these are very hard to assess, and at least there hasn't been many ways of quantitatively assess how good these are. So I think the community also should think a little bit about how do we benchmark machine learning potentials.
Yeah, thank you very much.
Other questions? Do you have any questions?
Hello.
Yeah.
Good morning.
Morning.
Yeah, very. Thank you for a very interesting talk. And my question is, I would like to know, you are mentioning the nuclear quantum effect.
Mm-hmm.
I am new to this computational work, but I want to know just what you have mentioned, nuclear quantum effect. Is it related to nucleation effect or something like that? Nucleation among molecules, something?
Okay.
Nuclear quantum effect.
Right. So the nuclear quantum, so we all see electrons as quantum mechanical particles, right? They are like wave-like particles, right? But typically when people talk about atomic nuclei, we typically approximate them as classical point-like particles, right, in classical molecular dynamic simulations. But you can imagine that many nuclei, such as hydrogen or lithium and helium, they are also very, very light, right? So they also behave a little bit like wave-like particles. right? So nuclear quantum effects basically is an umbrella term that describes the difference between the actual behavior of this light nuclei and the classical approximation.
Okay, thank you. Please share your slides. It look very interesting talk, your talk. Thank you.
Thank you very much, Bingqing. Any other questions? Okay. So Sunday has a question, one of my students. Sunday wrong.
Yeah, thank you for the presentation. Yeah, so my question is on the potential that you developed using the liquid phase of water. Do you think it would be good to use it to study water dimer, like dynamics of water dimer, hexagonal, all those hypothetical chains of water that we read in literature?
So I think it's very unlikely because so in our case, we only do a bulk liquid water, right? But I imagine that the dimer and this monomer and this cation, all these things happens in vacuum. And I have not done this myself, but I'm pretty sure that if you actually compare the environments of these, if you compare the environments of these water clusters and the ones here, they will be very dissimilar. So the machine learning potential train for our purpose will not be able to extrapolate to the gas phase clusters.
Thank you very much, Bingqing. Okay.
Yep.
Yeah. So let's think, if there are no more questions, then let's thank Dr. Bingqing once again. Thank you very much, Dr. Bingqing. Yeah. So the next talk will be by Professor Jörg Belle. We'll wait a few, so Jörg, please, you can show your slide, but we'll wait a few minutes to 10 o'clock. And then we'll start exactly 10 o'clock.
So I hope you can see it now.
Just coming up. It's coming up.
Yeah.
Yes.
Okay.
So we took it 5 minutes. Yeah. Oh, yeah, I know. She's on the other side.